Hi everyone, my name is Tushar Chandra. Today I will be giving a Let's Build a Model talk called Learning Bayesian Statistics with Pokemon Go. This is my first conference talk, so I'm very happy that you decided to tune in and I hope you enjoy. So I am a senior data scientist at Nielsen in Chicago, Illinois. In my day job, I get to use Bayesian modeling to develop next generation audience measurement models. And so I've been doing Bayesian modeling for about a year now, and I'm really excited to share some of the things that I've learned. I love cats, chai, and video games and fall weather. This is a picture of my kitten Rhubarb sitting in the hood of my sweatshirt. And I have a personal website, tusharc.dev, where I blog about HCI research and data science. I just write about things that interest me, including Bayesian modeling. And so you can find resources for this talk, including the code, the notes that I was using as I'm reading this out, and other resources for learning about Bayesian inference on my website. So in this talk, we'll be developing basic Bayesian models using PyMC3. These models will be motivated by questions from Pokemon Go. And the reason that I chose Pokemon Go is because it's kind of inherently a probabilistic game. There's a lot of things that the developers leave to chance, for better or for worse. And there's a lot of natural questions we can ask to help us learn about the game. I'll be giving some background about Pokemon and Pokemon Go. So if you don't know anything about them, that's totally fine. Pokemon Go is a mobile game that was released in 2016. In this game, you see a map of your real world location. So those are like real streets around me in Chicago with virtual creatures that are called Pokemon around them. So that's a little Doduo on the map, that two-headed bird guy. So if I click on him, I would be able to encounter him and possibly catch it, which means I would just add it to my collection. Shiny Pokemon are specially colored, and they're very rare, and they're sought after by collectors. Again, Pokemon's a collection game, and so there's a lot of hype around shiny Pokemon, and a lot of people really like collecting them. In the top picture, you have a regular Ho-Oh, and in the bottom picture, you have a shiny Ho-Oh. And so you can see it sparkles and is differently colored. So there's lots of ways to get them, but we do know that they're always rare, and we don't know exactly how rare they are. So this question of how rare are shinies is the operant question in our talk. You may be wondering how this relates to Bayesian inference, and one of the things that I'm going to try to drive home is that Bayesian inference is about asking the right questions. So once you ask a question, you can make a hypothesis, you can try and guess what your plausible answers to that question might be, and then importantly, you can collect data to answer that question and build models to try and get closer to an answer. We'll never be able to answer the question of how rare are shinies exactly unless we have access to the game developer's code or if they tell us. But as just normal players, we can make hypotheses and collect data about it. So let's get started with a simple example. Shiny Rayquaza is a very popular Pokemon and a very popular shiny. You can see a picture on the right. And it was released into raid battles in August of 2019. So let's suppose that my friend group over the course of the week or two that it was around did 44 raids and got 2 shinies out of it. What do we think the shiny rate is? So naively, you could say 1 in 22, 2 over 44, just under 5%. And that would be that would be a pretty reasonable approximation. Like, it's probably pretty close to the truth. More battles and more data would always help us to get to a better answer. But there's nothing wrong with estimating it as 1 in 22. But we can develop little more powerful estimates using Bayesian inference. So one of the reasons that the PyMCCon organizers created these kind of let's build a model talks is to help people who have experience in Bayesian modeling walk through their thought process when they're approaching new problems. And so that's what I'm going to do today. So this is my approach to Bayesian modeling, and it's not the only approach, and I don't even follow it all the time, but this is like a relatively principled way to get started. And this is what I'm going to walk through a couple of examples today. So the first step is to describe the data generating process. And what this means is figure out the process that would have generated your data. I'll walk through this in a lot of detail in a minute. Using that, we can sketch out a model and then fill in the gaps of that model. And then after that, we can just iterate to make it better. I like to describe problems in terms of the process that could have generated our data. There are a few reasons that I want to do this, but in general, it helps me lay out my assumptions. It helps me to lay out what assumptions I have about the problem and about our data. It can help me to identify points of misunderstanding or points where I'm unclear about how a problem is actually set up. And eventually, it does make building a model easier. This doesn't take long, and we end up doing this implicitly when we make a model anyway. So I'm going to do it now and walk you through what that means. So let's suppose that there's some probability, p shiny, of seeing a shiny Rayquaza. Maybe it's 1 in 10, maybe it's 1 in 20, we don't know. But, given that probability, we saw 2 shinies in 44 attempts. If that probability is constant across attempts, and if those attempts were independent from each other, then that's a binomial distribution. If that probability wasn't constant, or if those attempts weren't independent, then it's not a binomial, and we can come back to that, what that'll look like later. But for now, let's assume that that is the case. So let's start with our, oops, this is going to be a markdown cell, so we're off to a good start. Rayquaza model. Make Rayquaza model. So what I like to do is sketch out what the different probabilities and random variables are and see what they mean, see what they put placeholders for them, okay? So the first thing, based on the previous slide, is p shiny equals something. This is going to be our prior, it's coming soon. And then the next thing we have is the number of shinies, something else. That's our first model. That's not very much, but we will get to it soon. So we knew that number of shinies was a binomial distribution, so let's fill that out. And we're going to import PyMC3 as PM. I can just run that. Let me restart my kernel. Oops. Okay. And that's, this is our model sketch. We had our probability of being shiny right here, and then we have our observations, which are binomial distributed. Okay. So according to the PyMC3 documentation, we want distributions, and we want discrete, and we want binomial. So according to this, it takes n and it takes p. So n is the number of attempts, and p is the probability of success. So based on that, we can go here. Let me make this bigger also. N was 44. I'm going to come back to why we need this. So what this is saying is that this random variable has the name number of shinies. This string doesn't have to be the name as the name of the variable because Python doesn't know what your variable is actually named, but it's generally good practice too because otherwise things can get confusing. The number of observations is 44, the probability of success is p shiny, and optionally, if we have observations, which in this case we do, we can put those in. So observed equals 2. I'm going to make this function able to take a variable number of shinies, and we'll come back to y actually. Let's just not include a default value, and we'll come back to y later. But so we've got this, okay? That's done. So PyMC3 also requires us to wrap our model in a context manager. What that looks like is this with pm.model as model. We indent that, and then we can return it. So the reason that we do this is because PyMC3 will create this model kind of wrapper object behind the scenes. That's what pm.model, that's what that call does. And then when we are within that context manager, PyMC3 will add all of our random variables to that model behind the scenes for us. So by saying this, we're saying, hey, by saying this with pm.model, we're saying, hey, PyMC3, please create a new model for me, and we'll call it lowercase model. And then we'll add this p shiny random variable to it once we fill it out. And then we'll add this number of shinies random variable to it. And then we return it. We have a function that returns it. So let's talk about this p shiny term. In Bayesian inference, we will call that a prior. And our prior is what we think is plausible in the absence of any data. So without having any data here, what that means is if I told you that shinies are rare, what do you think that means? There's a lot of things you could think that means. It could mean that all shiny rates from 0 to 1 are equally likely. I don't necessarily think that's a great prior, but it's fine. I don't necessarily think that's, that doesn't mean it's rare. That means you placing equal probability on every shiny rate, whether it's 0.1 or 0.9. So that's uninformative and it's justifiable, but there's other options as well. Another is that from 0 to 0.5 is equally likely, but above 0.5 is impossible. And that's placing a really strong prior, like infinitely strong, on the idea that you cannot have a shiny rate of 0.6 or 0.7. And another prior that's kind of in the middle is that your shiny rate is decreasingly likely as you get closer to 1. All of those are plausible. I don't actually recommend mucking around with priors right now. So I'm going to pick beta 1, 2 arbitrarily, according to my slide deck. So let's go back to our model. So here what we're going to do is fill in this gap. So we're going to do pm.beta. We're going to call this pshiny and say 1, 2, and return the model. That's it. That's our model. Okay? So what comes next is what we call Markov chain Monte Carlo. And Markov chain Monte Carlo is how we go from our model, which are our random variables, p shiny and number of shinies, plus our observations, which is the number of shinies that we actually saw, to what we call a posterior distribution. There are lots of ways to think about this, but one of them is saying that it combines your model and your data and then infers the most likely distributions of your random variables. You can condition your model on the data. You can use your data to learn about the model. You can run your data backwards through the model. And I also want to say that if you don't actually know what MCMC is coming into this talk, I don't expect that like 30-second explanation to make it made sense for you. But there's a lot of great resources out there on the web. I cataloged a bunch on my website, tusharc.dev/posts/Bayesian_resources.html. I have 4 links in this article, and there's 2 books, Andrew Gelman's Bayesian Data Analysis 3 and Richard McElrath's Statistical Rethinking, that are all excellent resources for learning about Bayesian inference and MCMC. But again, MCMC says, given the model and the data, so our model is this stuff, and our data is this observed number of shinies, run MCMC, and then we infer the most likely distributions of the random variables. So in this case, our random variable that we want to learn the distribution of is p shiny. So we put a beta prior on it, saying that without any data, we think it's distributed according to beta 1, 2. Now that we have our data, what do we think the actual distribution in practice is? So let's just run this, okay? So let's do sample, idata equals sample, make Rayquaza model with n shinies equals 2, which is what we said originally. Okay, and so now we're going to see MCMC go. And once it's done, I'm going to show you what this idata object looks like. So what we're doing here is we're waiting for Markov chain Monte Carlo to run, and we're asking PyMC3 to sample this distribution for us so that we can get an estimate of what the posterior looks like. In practice, what we're going to end up with is 4 chains times 1,000 draws each, so we'll have 4,000 samples of what the random variable p shiny might look like. And here we go. This is a simple model, so it runs super quickly. So we have our RViz inference data. We have our posterior, and we have 4 chains of 1,000 draws each, and our variable is p shiny, which is indexed according to chain and draw. So if we click on this over here, whoops, we get what some of the samples were. So the first sample was 0.035, the second sample was 0.058, next sample was also 0.58 or 0.058, and that just repeats. So we can plot this. RViz is a plotting library. So what I'm going to do is do az.plot trace idata. And we get this. So on the left we have this, we call it a trace plot. Its title is called, this is the posterior distribution of p shiny. This is it. Like, this is what we think after running MCMC. This is what we think the distribution of the probability of the shiny is. So we think it's slightly under, most likely slightly under 0.05, but there's a ton of likelihood all the way as low as 0 and as high as 0.15, almost 0.02 or 0.2. So what this means is that we think the shiny rate could plausibly be anywhere between 0, like slightly above 0 and, 0.15 maybe. But that's it. We did it. That is our first model. I'm going to show you how flexible these kinds of models are, because we can just change this number of observations, okay? We can just change this to 0 or 4 and see what we get. And I think that's useful because it shows off how much we can get out from just a few lines of code. So let's do 0 shinies. I'm just going to take this again. N shinies equals 0, plot, trace, idata, and then I'm going to do 4 shinies while I wait for that to run. N shinies equals 4, not 40. So one of the reasons that I also like Bayesian inference is because it can help you estimate the probability of really rare events. if we got 0 shinies out of 44, the conventional wisdom would be to say that the shiny rate is 0. But as we're about to see here, there's actually a very high likelihood that the shiny rate is non-zero. It could be 0.02, and we just like 1 in 50, and we just got unlucky. If it's 1 in 50, we wouldn't necessarily expect to see a shiny right now. And it could be as high as like 0.08, and we just got unlucky. Okay. So what we see is that, yes, the most likely value of the shiny rate is 0, which is consistent with what we expect, but there's still a lot of probability density over here. It's still possible that there is a non-zero shiny rate, and we just got unlucky. When we have 4 shinies, the peak of this distribution is at like 0.08, 0.09, which is consistent with what our expectations are. We expect roughly 10%. And there's likelihood as low as 0.02 and as high as 0.20. This helps us to quantify uncertainty a little bit more explicitly than we would be able to otherwise. We can literally show this distribution to someone and say, this is what we think the shiny rate is. Based on our 4 shinies out of 44 observations, we think the shiny rate looks like this. It could be 0.05, it could be 0.08, it could be 0.15, we don't know, but we think all of those are plausible values. And that's one of the reasons why Bayesian inference is so powerful.
Next thing we're going to do is talk about how we can use Bayesian inference to update our models and our beliefs over time. We're going to do this with crowdsourced research data from an organization called the Sylph Road within the Pokemon Go community. So they are a group of player researchers who gather data about shiny rates and other mechanics, like hatch rates. On this slide, you can see some of the press releases that they've put out, which is one for the Johto Journey event, where they ask what were the Centroid and Gligar shiny rates, what were the Adventure Week shiny rates, etc. The way that they do this is by collecting a large number of players and having them each write down the number of encounters of a certain species they have and the number of shinies that they see. So someone here saw 661 Kricketot with 4 shinies, someone else saw 155 with 0. Over time, you can use this to get a decent estimate in aggregate of the overall shiny rate. Over time, a bunch of players in the Pokemon Go community started to believe in this 1 in 150 shiny rate for certain types of events. So these are Reddit comments from the past year from a Pokemon Go Reddit community, and a lot of people believed that the shiny rate for certain events, including one that ended just yesterday, was 1 in 150. We're going to study the extent to which this is true. And to do this, we're going to use data from the Sylph Road itself, and we're going to conduct our own analysis because replication experiments are valuable. And I've taken the time to collect this data ahead of time, and you can find that on my GitHub with the username tuchandra/PyMCCon2020talk, and the file name is rates.csv. So it looks like this, where we have number of encounters, number of shinies, the date, the name, and a URL to the source, and that's just sitting in the repo. We are going to start with a new notebook called livesylph.ipynb. I guess I'm not going to name it. Whatever. So this is going to be the Sylph shiny rates model, and I'm going to start with some imports. So all I've done here is import a couple of things, and we're going to use pandas to just read in the data to show you what that looks like. So here you have the columns that I said before: URL, date, name, number of encounters, and number of shinies. What I'm going to do next is create a helper function that, just given this data frame, will return the number of encounters and number of shinies. So what we're going to do now is go through our priors and build a model. So the data generating process is going to be the same as it was before, right? We have some probability of seeing a shiny, and then for all of these thousands of attempts, if they're independent and if each attempt is independent, and if the shiny rate is constant across attempts, then we're going to have some number of observations that follows a binomial distribution. Oops. Yeah. So we're going to do what we did before with pm.model as model. P shiny equals pm.beta. I'm going to show that this prior is reasonable in a minute, but for now, trust me. And the first Pokemon that we saw was Psyduck. So what we've done here is we've created a pm.beta, which is our prior. It's a beta distribution over the probability of encountering a shiny. We've gotten the number of encounters and the number of shinies for Psyduck. This is now a tuple of 2 integers. And we're going to put the first one as the n for the binomial and the second one as the observation. So if we just run this, we should be able to define a model. So what we're going to do now is verify that our priors are reasonable, and to do this we're going to do something called prior predictive checks, which kind of confused me when I was learning. So prior predictive checks are just a way, if you run your model forward using only your priors, like sampling only from your prior distributions, you see what the output is, and you verify that your data at least looks reasonable, looks kind of reasonable. So the reason that we're able to do this is because one of the things that I mentioned earlier is that we want to think of our model as a data generating process. So given the fact that this model will generate observations for the number of shiny Cydex we encounter, let's look at what those observations are with only our priors. So we can do this with PyMC 3. And we can use rvis to plot the prior density here. There's a bunch of keyword arguments that I've kind of figured out ahead of time. So I don't expect anyone to be able to come up with those keyword arguments by themselves. I certainly didn't, but it was just a lot of trial and error that wasn't worth putting into the final cut of this talk. So over here we have a density for the probability of shiny. I'm really sorry that the text is so small, but you can see that you might be able to see that it's centered around 0.006, and the number of Psyduck, the number of shiny Psyduck can range anywhere from like 15 to 150. And again, we had like, I don't know, 10,000 observations. So this presumes a shiny rate of somewhere under 1 in 100. One thing that I want to note here is that it's really hard to see what the actual shiny rate of 1 in n is. And the reason is because we did everything in terms of the fractional shiny rate, but we can actually invert that and plot what the like 1 over x value would be itself. We can do that in PyMC3 using this nice deterministic construct, so I'm going to call it the rarity. But in PyMC3, you can have deterministic functions of your random variables and include them in things like your model and your prior predictive and your posteriors. So the rarity is simply 1 over p shiny. And if we do this, we can add rarity to the prior predictive. And what we see now is that the rarity is centered around 1 in 150, with likelihood as low as like 1 in, I don't know, 1 in 80, or 1 in 80, and as high as almost 1 in 350. So that's a very non-informative prior, but that's fine for this problem. We have our prior predictive checks. We are ready to start sampling using MCMC. So I'm going to lift the sample function that I used last time. All this does is use Markov chain Monte Carlo for 2,000 draws, 1,000 tuning steps, and 4 chains, and convert it to an rvis inference data object and return it. So all we have to do is say idata equals sample. We called it model above, and then we're going to plot the trace using rvis. So this is going to take a minute to run, and once it's done, what we're going to see is a posterior distribution for what we think the shiny rate of Psyduck was. This is an example of how our beliefs have changed over time. So prior to having this Psyduck event, we believed that our shiny rate was this, somewhere between like 1 in 80 and 1 in 400. And after MCMC finishes, we will have used our data to update our beliefs, to update our priors into a posterior distribution. So we're almost done here, and what we get is that the rarity, the like 1 over x, is roughly between, at lowest is like 1 in 100, and on the other end it's like 1 in 200. So remember that our prior was also centered around 1 in 150, but now we see our posterior is centered around 1 in 140. And the reason for that is because the shiny rate that was observed for Psyduck was like 1 in 138. So you can see that our posterior isn't actually exactly centered at what we observed for Psyduck. It's centered a little bit between, it's centered really close to that, but it's centered a little bit north of that and still closer to the prior. That makes sense because our posterior is a combination of our prior and our data, and not just our data alone. So the next thing that we want to do is update our beliefs about the shiny rate based on the event that happened in April 2019. So after January, we think that the rarity was around 1 in 40. After April, we had an event for Diglett and we had an event for Shuckle, so let's see what those are. So I'm going to write out the next 2 sample statements in our model. I'm going to type this out and then just kind of skip ahead in the video to where it's finished typing because it's the same structure as what we did before. Okay, so now we have our model where we added Diglett and Shuckle as binomial observations, and we're going to use the same sample function from above to get a new posterior distribution. And while that runs, While that runs, I'm going to get the next plotting function. Here we are. So the rarity is now still around 1 in 140, but we're more certain about it than we were before. The lower bound is around 1 in 120, and the upper bound at 1 in 160. This is good. It means that we took advantage of the data that we had. We had several tens of thousands of observations here, and we took advantage of it, and we're able to get a much tighter bound on the rarity. We'll note that 1 in 150 looks even less likely than it did before as well. So the next event was in June 2019. We had a Horsey event, and let's just add that to our model. And we're going to see the same. We're doing the same thing, right? We're going to do with model and add the Horsey and create a binomial likelihood for it and sample and then plot the trace. So at this point, it's June 2019, and we've seen a Horsey event, and now we believe that the rarity is somewhere a little more common than 1 in 140, maybe like 1 in 137. But again, anywhere between 1 in 130 and 1 in 150 is still very plausible. The Horsey event didn't do that much to change our understanding of the shiny rate, but it did change it a little. And the reason it didn't change, part of the reason it didn't change it that much is because we have so much data from before that the Horsey event isn't really moving the needle that much. If we had tens of thousands of observations, it would, but I think Horsey only had, like 7,300, compared to Diglett and Shuckle each having like 10,000 each. And so this data isn't as important as our previous data was. So the next few events, there's Niederan and Sneasel, there's Polywag, there's Gligar and Yanma, and there's Oddish. So I'm going to go through these really quickly. I'm going to type it out and then skip ahead in the video again, because it's the same story. We add those binomial observations to our model, and then we sample, we're using Markov chain Monte Carlo, and then we look at our posterior distribution of what we think the shiny rate is. Okay, so what we've finally done here after all this typing is we've added the last 7 species to our model at once. We added Nidoran, Sneasel, Polywag, Gligar, Yanma, and Oddish. This last one is Oddish. And we've added all of them to our model, same way as before, where we get the data, we get the number of encounters and the number of shinies, and then add a binomial likelihood function to our model. That tells us within, in our data set, we saw this many Oddish with this probability of shiny, and observed this many. So we're going to wait for this to sample, this will take a minute, and we're going to plot our final trace plot before making some final comments about some of the assumptions that we made that underlie this model. So what we have here is our final posterior distribution, essentially. We believe that the rarity is a little bit, probably most likely a little bit above 1 in 130. It can go as low as maybe 1 in 120 and as high as, 1 in 145. At this point, I would feel very confident in saying that the shiny rate isn't 1 in 150 and is in fact a little bit higher than that, a little bit more common than that. In general, though, I would say to avoid giving point estimates, and I would say it's most likely that the shiny rate is around 1 in 120 to 1 in 140 or something like that. Giving point estimates creates a certainty that we want to avoid because we can never know the shiny rate for sure, and instead we should try to speak in ranges and convey this uncertainty where possible. The thing that I want to talk about is the chance that we're wrong about this. Okay, I want to talk about what could have made our model be incorrect, like what could have made our posterior belief about this shiny rate be just wrong. So one way is poor data collection, right? It's really easy to make mistakes when you're writing down hundreds of encounters, and even if you're just keeping tally marks, it's really easy to forget an encounter sometime, or forget to make note of a shiny or miscount something, right? If your data is bad, your model is going to be limited by your data. That's kind of a fundamental fact about Bayesian inference. It's a fundamental fact about statistics. Like we can only make conclusions as good as our data is. And the other major way that our model could be wrong is if these events didn't have the same shiny rate. So what we assumed when we were building this model implicitly was that every single one of these events had the same shiny rate, and the community believed this to be 1 in 150. But it could very well be the case that Horsey had a shiny rate of 1 in 150, but Oddish had a shiny rate of 1 in 120, and Sneasel had a different one, and Gligar had a different one, and all of them, whatever, We built our model with the assumption that they're all the same, but if this isn't true, our model is bad. In the world of Bayesian modeling, we call this a pooled model, and this is equivalent to how if we had pulled together all of the attempts and summed up all the attempts and summed up the number of shinies and just trained a model based on that. I'm going to do that here, but again, I'm going to skip forward in the video while I type out the code and explain what it's doing while I sample. Okay, so we have a model sampling now, and again, what we did is we have our p shiny with a beta prior with the same parameters as before, and we have our rarity, which is a deterministic function, just 1 over the shiny rate. And then we have our binomial likelihood, where the number of data points, the number of trials, is just the sum of all the rows in the data frame, and likewise for the number of observed shinies. So we sampled it and we plotted the trace, and we see that our rarity is centered a little bit over 1 in 130, which is consistent with what we observed above. The reason that we didn't do this is because that kind of missed the point of this exercise, which was updating our priors and updating our beliefs over time. So the point of this activity was to see that, okay, if we had an event in January, what do we believe the shiny rate is? Now we have an event in April, how do we believe the shiny rate is now? And to just do that throughout all of 2019 and consider all of those events that happened one at a time. But there are other ways that we could model this. In the world of Bayesian modeling, we might say that we want to use a hierarchical model, and I'm not going to go into the details of this talk, but what this loosely means is that all of the species have a shiny rate that's related. It might be drawn from the same pool, but it's not the same. So this allows for interspecies variability. This allows the shiny rate of potash to be a little bit different than the shiny rate of glycar without trying to match each individual data point. And again, the details are out of scope for this talk, but if you want to learn more about them, hierarchical models are kind of the bread and butter of Bayesian modeling. So there's a lot of great resources out there on the web. So let me end with some takeaways about what we were doing here. So the main one is that updating your beliefs over time is the heart of Bayesian inference. That's what this is all about. You want to figure out what your priors are. We all have prior beliefs about how the world works. We call them assumptions a lot of the time. And then we want to build a mental model of whatever it is we're interested in, collect some data, and use that data to update our priors into a posterior. That's it. And then we use the posterior as our next prior and repeat kind of indefinitely. That's how we think about the world, and that's how we think about Bayesian inference too. Updating your beliefs over time in the presence of new data is the heart of what all of this is about. And the other thing is that communicating uncertainty is really, really hard. So the players who are saying that the shiny rate is 1 in 150, we can never prove that they're wrong. We can be fairly certain that they're wrong, but even then, we can't come up with a point estimate of our own shiny rate. Like, I could tell you that the shiny rate is 1 in 130 based on this plot, but that is doing a disservice to all of the work that we just did to narrow down the shiny rate range from 1 in 120 to 1 in 140. I think this is one of the reasons that Bayesian inference is often seen as kind of inaccessible to beginners, because it's really difficult to talk about uncertainty in this way. It's really difficult to admit that you don't know something for sure, and a lot of institutions and a lot of people in society don't really reward this kind of uncertainty. But ultimately, it's more truthful and it's more accurate than anything else that we're able to do. Talking about uncertainty in this way, saying that the shiny rate is between 1 in 120 and 1 in 140, is still useful, and it can help us to level set our expectations and make better decisions about whatever it is we're interested in. Right. For our last model of this Let's Build a Model talk, which has turned into Let's Build Several Models talk, we will be doing a model about change point detection. So the question we're going to ask is, did a hatch rate change over time? This isn't about shinies anymore, but it's the same kind of randomness where players don't know the actual true value of a probability and just have to kind of do their best and play, and in this case, spend a lot of money to get the result that they want. So a couple of months ago, we had an event called Dragon Week. And this was a very anticipated event where Dragon-type Pokemon could hatch from eggs. So again, this isn't about shinies, but Dragon-type Pokemon hatching from eggs is, there are also sufficiently rare things in this event that we care about. So on the left, you have 5 species, Dratini, Trapinch, Bagon, Horsey, and Swablu, and they were all very common during the week. They were all very common in the wild. They have all been in the game for a couple of years now, and no one really cares about them. You have Gibble, which is over here. It's this little land shark guy, and he was pretty rare. You have Dino, who is extremely rare, and is just like, it's just very hard to find in the game. And it was advertised by the game developers prior to this event that Dino would be the highlight of this event, that you could hatch it from eggs if you were lucky, and a lot of people were really looking forward to this. You can probably tell where this is going, and so a couple days into the event, the same Silk Road research group hatched 266 eggs, and not a single one was Dino. So at this point, we're like, oh no, what's going on? It got media coverage, and all of a sudden, more Dinos started appearing. So after 2 days of not hatching one, on the third day they hatched one, and on the fourth day they hatched 7 of them out of 181 eggs, which wasn't that much more than before. So almost everyone has started to believe that the hatch rate changed midway through the event. And I personally believe that too, but I'm going to show you how we can come to this conclusion using Bayesian inference. So what I'm going to do is, I'm going to actually build a model that's kind of inspired by one of the best books on Bayesian inference, which is called Probabilistic Programming and Bayesian Methods for Hackers. This is by Cam Davidson-Pilon, and it was ported to Python and PyMC3. If you just search the title of this book on Google, you will find it. And I'm going to I'm going to adapt one of his models from chapter 1, where he was interested in finding out if the number of text messages that he sent on a particular day changed at any point in time. So that was a Poisson likelihood. This is going to be a binomial likelihood, but the same principle applies. So what we're going to do is we're going to suppose that in these 8 days of data, that the hatch rate changed, that sometimes 0 is less than tau is less than 7. Okay, so on one of those days, before that, there was a hatch rate p before, and after that, there was a hatch rate p after. And given that hatch rate, we know how many eggs we hatched, and we know how many of those were Dino, and so that's a binomial likelihood if we, again, assume that the events are independent and that the shiny rate didn't change, which at this point is a very big assumption. But here what we're assuming is that the shiny rate didn't change within a particular day, which, again, like, it had to, unless the game developer switched it off at midnight, it had to have changed within a particular day, and so this assumption doesn't hold up, as we're going to see, but it's good enough to continue, and at least to build a model with. So let's code. Okay, so I'm going to start with some, this is the notebook called Dragon Week Live. Dragon Week. Okay, I'm going to hide this, and I'm going to zoom in. Great. So let's start with some imports. RViz we're going to need. I have data, again, in this dragonweek.csv file. This is available on my GitHub. And then I'm going to just I'm just going to make the columns a little bit easier to read. What do we get? Okay. So here we see the 7 different species in a row for total, and the 8 days on which this event occurred. But, so on Dino, for Dino, we see we hatched 0, 0, 1, and then 7, 6, 3, 5, and 1 during this event, and here are the totals for the eggs. So let's plot this, okay? Number of Dino hatched, again, 1, 7, 6, etc. Proportion of Dino hatched, also, again, we have 2 days of 0, 1 day of 1, and then suddenly the rate goes way up. So this is not looking good for the hypothesis that the shiny rates were the same throughout the event. But let's go back to the model specification, and I'll show you how we build this in PyMC3. Okay. Okay. So again, we always start with pm.model as model. And so again, we declare the model object, and we declare it as a context manager, and then this lets PyMC3 add the random variables to the model behind the scenes. So we're going to have p before equals pm.something. We're going to have p after, which is the same. Then we're going to have our switch. So I'm going to go ahead and fill this in right now. For the switch, we know it's going to be on a day between 0 and 8, or 0 and 7 inclusive. So PyMC3 has a discrete uniform distribution. So our prior for this is going to be that it was equally likely on any day of the event. So we're going to say it's uniform switch between 0 and 7, and I'm going to hard code those numbers, but in practice you should use, like, max of the array or min of the array or something. Okay. So before we go on, let's talk about what these pm.somethings should be. So that's a question of what our priors are. which we've talked about before. I said before that we shouldn't mess around with priors too much, but we do need to choose something. So in practice, what we know is that shinies are rare. Previously, I said that you could choose any number of priors for shinies being rare. We know that Dino is rare too. So we could probably choose one of the same priors we did before. And in practice, what I always do for for the priors for probabilities, I almost always just choose a beta prior because it's simple. And in the nice case, we're using a beta prior and a binomial likelihood. The beta binomial is very well known and very well studied. That's not what we're doing here, but I like beta priors. Okay, so we're going to do 1, 2. So now what we're going to do is something straight out of the book, Bayesian Methods for Hackers, where we essentially so for each day, we want to pick the right probability for each day, okay? So let's start with our likelihood because that'll make this a little bit more clear. Cool. So this probability we have to have a value for each of the 8 days of the event. So it needs to be a NumPy array of shape 8. We also need to make sure that it's the right probability based on the switch. So it's p before whatever the switch is, and it's p after that switch. So the first thing we need to recognize is that p before and p after are both scalars. So we're going to have to create an index. And then what we're going to do is we're going to use a pm.math.switch statement. So let's do pm.deterministic again. Again, this just adds deterministic variables to our trace. So note that p before, p after, and switch are all random variables, but the actual probability on a particular day is going to be a deterministic function of those. Because given the day, you check if it's before or after the switch, which is deterministic, and then you choose p before if it's before and p after if it's after. So we go from these 3 random variables and then combine them in a deterministic way. So what we're going to do is we're going to do pm.math.switch, and we're going to say you switch on the condition that your switch random variable is greater than or equal to your index. So switch is this. And if it's greater, if the switch happens after the current point in time, you choose p before, and if otherwise you choose p after. So now let's run this and see what works, see what happens. Hopefully nothing happens because this should just declare, yep, okay, so the model is declared. So we're going to do 2,000 draws, 1,000 tuning steps. I'm going to do 8 chains this time for reasons that'll become clear in a minute. Okay, let's run this. Okay, so what you're seeing here is PyMC3 is telling us we're using this compound step, and the reason is because the no U-turn sampler nuts, which is what PyMC3, Stan, and other probabilistic programming libraries use, only works on continuous variables just because of the way it's designed. But switch is a discrete variable. It's between 0 and 8, and so we have to use a Metropolis sampler. Metropolis is generally less efficient than nuts, and in practice you probably shouldn't use it unless you know their choice, which is what we have here. But what we're going to see if this ever runs, there we go. What we're going to see is that this isn't going to go well, and we're going to encounter something called divergences, which you can see here. So divergences are very, very bad in the world of Bayesian inference. What it means is that your sampler did not, it means that your sampler, as it was jumping around the posterior distribution, kind of went off into nothingness, and just I don't know, it means that the sampler didn't do a good job of exploring the posterior distribution. It also means that you shouldn't trust your posterior. So what we see is there were 32 divergences here, 1 divergence there, 3, 14 on the different chains. We just see a plethora of warnings here, and we're going to see this in our trace, where this looks way worse than what we saw before. And so what we can see is, can I zoom in more? No, not really. Sorry. So what we're going to see is that this sampler is not very well, we call it well mixed. So ideally you have that fuzzy caterpillar shape like I described before, and we kind of see it with p before, where it's just all the chains are indistinguishable from each other. But if you look at switch, it's just kind of getting stuck. One of the chains is just kind of chilling there and not exploring the sampling space very well. And then these like thicker black bars are regions where the sampler goes off. So you can see this particular chain is going off to like 6, 7, 8, 4, 5, 6, 7, and just kind of getting stuck there. So it's just not doing a very good job. And these thicker black bars are definitely reason to be alarmed. At this point, when I was building this talk, I was like, oh crap, I can't use this example anymore. And so I did some Googling because in the book Bayesian Methods for Hackers, the author has no problem using the sampler there. Bayesian models can be super finicky, and once you see divergences, it's usually a sign that your model is misspecified. In this case, it wasn't, because I did some debugging and noticed that the model was actually fine. But what I did find was other examples of Bayesian change point detection. So this is by Chad Scherer on their blog that I found on Google. And they're trying to do the same thing with estimating the frequency of coal mining disasters over time. And so I read through this post, I was like, this sounds pretty similar to what I'm doing. And what they say is, let's use slice sampling. For now, don't worry too much about why this is a good way to go. So they never went on to explain it, which I was kind of confused by, but I tried it too. And so, lo and behold, if you change step to pm.slice, I'm going to move this onto a new line so you can see everything. If you change step to pm.slice, suddenly things are going to look a lot better. And I went to the Wikipedia page on slice sampling and didn't super understand it, but I feel like even if I did, its details would be out of scope for an introductory level talk like I'm giving right now. So maybe I'll learn it someday, and maybe I'll give another talk at PyMCCon next year, who knows. Once this runs, we're going to see a sampler, or we're going to see the posterior distribution. I'm actually going to change this parameter. No, I won't. Okay, we'll just let it run. It's going to take a bit. So what we're looking for is evidence that P before and P after have different posterior distributions, right? So if we see clear evidence of a switch and we see clear evidence that the posterior distribution of P before is different than that of P after, then we have reasonable belief that the shiny ray changed over time. And what we're going to see is that. So here's the switch statement where we see there's a little bit of likelihood that the switch happened at day 1, and a lot that it happened on day 2. P before is very low, between 0 and 0.005. P after is higher, but still low, but at least an order of magnitude higher. And so we can see that on day 0, day 1, day 2, day 0 and day 1 are fine because this is roughly the same as P before, because we know that the switch didn't happen on day 0 or day 1. Day 2 is super interesting because we almost see this bimodality, where we're mostly confident that the shiny rate was close to 0, but there's also a hint of likelihood here that the shiny rate increased. And then on days 3 through 7, we're very confident that the shiny rate is big, the shiny rate is higher. So let's look at another way of plotting this. I'm going to change this to... Let's look at another way of plotting this. So we can use the trace samples directly. And what we can say is, so here the bimodality becomes clear. So this is really interesting. So before, we see this is what we think the posterior distribution is before the switch, and this is what we think it is after. So these are very, very different, and this to me is almost ironclad evidence that the shiny ray changed in the middle of the event. So I want to try another species quickly as just like a test to make sure that our model wasn't self-fulfilling. Like what if us building the model that encoded the switch put too much structure on the problem such that the sampler had no choice but to find the same probability for both? What if us putting the switch statement in the model forced the model to kind of encode this structure that found a shiny rate before and a shiny rate after? Like what if we do this? So let's try this for species that we don't think the shiny rate changed and see if we get different results. Okay, so I'm going to go through this really quickly because the model is literally the same. I'm just changing the observation. Okay, so model, I'm going to change this to Gibble. And then I'm going to take the samples. I'm going to take the sampling. We're going to use the same sampler here. Okay, and then what we're going to do is make the same plot. I'm going to actually start sampling, and then we're going to make the same plot. And then we're going to do the same plot here. We want Gibble, Gibble, Gibble. Okay. So the reason that I want to do this is because it's really important to test out, I don't know, it's really important to question our assumptions, right? I've said this a couple of times, and here's another example. So when we built this model, we kind of made the assumption that there was a switch, right? So there's a couple of ways to test this out. We could build a model where we see that there isn't a switch. Like we could build a model where we just fit one probability over all 8 days. In practice, I think that would I did this, and in practice that just shows like the kind of mean of the different probabilities, and it isn't that informative. But I think more interesting is to look at a different species where we don't think the shiny rate changed and see what we get. So let's build the same model, and if the shiny rate didn't change I keep saying shiny rate. If the hatch rate didn't change, as we think it didn't for Gibble, then we'll see something interesting like this, where we see a pretty simple distribution over the switch. It's not certain that the switch occurred, right? Like there's likelihood on all 7 days that the probability changed on that day. And if you look at the posterior distributions for P before and P after, they're actually the same. They're actually like centered around the same place, like 0.1. And if you plot all of the days' probabilities on top of each other, this is basically unimodal. And so if you look at this plot, oops, I need to change these axes bounds, 0 to 0.3. I'm going to make this higher. If you look at this plot, you see that the histogram of probability before and the histogram of probability after are different, but like almost entirely on top of each other. This plot shows that like before the switch, we think there's a little bit less likely. After the switch, we think there's a little bit less likelihood, around 0. But I think the most important point is that the switch, it's not clear that a switch occurred because the model is not confident that a switch occurred on any of these days, whereas for Dino, the model was very confident that the switch occurred on day 2. So that's that. This is that's the hatch rate for Gibble and the hatch rate for Dino. Bayesian inference once again led us to something that was pretty challenging to understand before. Like you can look at the data, you can look at the numbers yourself and convince yourself that the hatch rate changed, but using this kind of modeling approach is really powerful because you can test out your assumptions and just literally see what you believe the hatch rate was before and after. So in closing, I want to talk about a couple of things. Communicating uncertainty is really, really hard. There are a lot of really smart people in the world who have tried really, really hard to figure out how to communicate uncertainty better. And so my advice for this is to try not to give point estimates, try to speak in terms of probabilities, and try to show distributions of things that could happen, like try to show different outcomes of things that could happen when you have the ability to. That could be a series of talks by itself, so I can't go into too much depth here, unfortunately. The other one is question your assumptions. So there were a couple of places in this talk where we questioned the assumptions that we made that underlied our model. Here what we did was we questioned the assumption that a switch occurred and kind of reran the model for a different species where we're pretty confident that a switch didn't to see what we would get. With shiny rates, we questioned the assumption that we questioned the assumptions that every shiny was independent of each other. We questioned the assumptions that shiny rates were uniform across players. And it's really important to do this because Bayesian modeling forces you to lay out your assumptions kind of explicitly, but you can still hide behind your model. Where, yes, you have all your distributions out, but there's still a question of why you chose those distributions, why you chose your priors, etc. So you have to be really explicit about them. And finally, be open to updating your beliefs given new data. I've said this before, but this is the heart of Bayesian inference. Like, updating your beliefs in the presence of new data is how we learn about the world, and it's a natural way to think about statistical problems too. You have some hypothesis, you collect some data, you build a model, and then you update your beliefs based on what the data told you. That's it. That's Bayesian inference. That's the core of everything we did today. Thank you all for watching. I would love feedback on this talk. Like I said, this was my first conference talk. So my email address is on the slide, and I know there's also going to be a live Q&A on the PyMC Discourse, so my username there is Tushar Chandra. That's also my GitHub username, and on GitHub you'll find the code for all of the things that we went through here. And finally, on my website, I've put together a post about Bayesian inference resources, just like learning resources. These are some things that helped me to learn about Bayesian modeling when I was just starting out, and I hope that they can be useful to you as well. Here's what it looks like. So there's some books and papers, Bayesian Data Analysis 3 by Gelman, Statistical Rethinking, and the Probabilistic Programming by Cam Davidson. Some libraries, talks, other web resources, and just like worked examples about this. These were all useful to me when I was first starting out with learning about Bayesian modeling, so I hope that they are to you as well. Finally, I'm going to make another post that includes the slides and notes and materials and other things from this talk there as well. So thank you for watching. I hope that you are enjoying PyMCCon, and I hope that you enjoy the rest of the talks that you get to watch as well. Take care.